I am going to explain about Venturimeter. Venturimeter is a highly accurate discharge measuring instrument of incompressible fluid flow through pipe. Means it is used for to measure the discharge from a pipe of fluid which is incompressible. What is the application of this Venturimeter? It is mainly used in oil and gas pipelines, chemical processing, water treatment industries, and water supply system. Etc. are the application of this Venturimeter. And what is the principle on which Venturimeter is working? Venturimeter is working in the principle of conservation of energy for incompressible non-viscous fluids, that is on Bernoulli equation. According to Bernoulli equation, P plus half rho v square plus rho g is equal to constant. This is energy of a fluid that will be constant. So P is the pressure energy, half rho v square is kinetic energy, and rho gh is potential energy, means the energy due to height of the fluid is potential energy. Construction of Venturimeter. Venturimeter is containing of three sections. First is converging section, second throat, and third is diverging section. Converging section is, in converging section area is decreasing, and in throat area is constant, and in diverging section the area is increasing. So converging angle is about 20 plus minus 1 degree, and the deflection angle is, diverging angle is 5 to 15 degree, but 6 degrees preferred. And throat diameter is about to 1 by 4 diameter of the pipe to 3 by 4 diameter of the pipe, and diverging section is approximately 4 times of the diameter of the pipe, and this diverging section is larger than the converging section to avoid the flow separation. Here in converging section, cross sectional area is reducing in this section in the direction of flow. Hence, according to the continuity equation of incompressible flow, means density will be constant. So A1 V1 equal to A2 V2. Area is decreasing, so velocity will be increase. So as the velocity is increasing in the direction of flow, according to the Bernoulli equation, pressure will decrease. Means kinetic energy will increase and pressure energy will reduce. And here favorable pressure gradient is there, as pressure is decreasing in along the direction of flow, and here is smooth and attached flow will be there. Second is throat. This is minimum cross sectional area region. Here velocity is maximum and pressure is minimum, means velocity is maximum as area is minimum here, and the pressure is minimum because velocity is maximum. So all the pressure in maximum pressure energy is converted into the kinetic energy. So third point is, here streamlines and are straight here. Chances of cavitation is maximum because pressure is minimum here. So, and cavitation is where the pressure falls below the vapor pressure of the fluid. Diverging section, cross sectional area gradually increases along the direction of flow to restore the pressure lost in the converging section and throat section. It slows down the fluid to reduce the energy losses. In this region, gradually velocity will decrease and the pressure will increase according to the continuity equation and Bernoulli equation. So here will be unfavorable pressure gradient as pressure is increases along the direction of flow. Angle of divergence is usually kept between 5 to 7 degree to minimize the flow separation. So here I am going to explain this one. Here this is converging section, this is throat, and this is diverging section. Flow is taking from here to here. 1 is the point in converging section, 2 is point in the throat at the entry of throat, and 3 is at the exit of throat, and 4 is at the diverging section. So pressure at point 2 and 3 will be equal, and here pressure at P1 is P1 and 4 is at 4 is P2 P4. So P1 is greater than P2 and P4 is greater than P3. Converging section, Bernoulli equation in terms of head. Here I am writing the Bernoulli equation in terms of head, P upon rho g plus V square upon 2g plus z. So here in converging section, velocity increasing, so pressure energy is converting into kinetic energy. And here in diverging section, according to Bernoulli equation in terms of head, here P upon rho g plus V square upon 2g plus z. So here kinetic energy is decreasing as velocity is decreasing, so kinetic energy is decreasing and it is converting into the pressure energy. So pressure gradient here is P dP upon dx equal to P2 minus P1 upon x2 minus x1. So P2 is less than P1, so this term will be negative, hence dP upon dx here in converging section will be negative, that is favorable pressure gradient. And in case in diverging section, the pressure gradient is equal to P4 minus P3 upon x4 minus x3. So P4 is greater than P3, so this will be dP upon dx is greater than 0, means unfavorable pressure gradient or adverse pressure gradient. So this is adverse pressure gradient condition, so flow separation will take place here. So in the direction of, in converging section, in the direction of net force due to pressure gradient is in the direction of flow, so the effect of this pressure gradient will accelerate the flow. But in case of this diverging section, direction of net force is in the opposite direction of the flow, so this will retard the flow. And now I will explain what is the flow separation. When fluid flows under the adverse pressure gradient condition, the momentum of the flow reduces in the direction of the flow near the surface, that is near above the no slip. When the momentum of flow becomes 0, after that the direction of flow reverses, and this is known as point of separation of flow. After separation, huge losses will occur in this one. So we will assume the flow should be steady and along the streamline. Second, the fluid is incompressible and non-viscous. Third, 1D flow. And what will be limitation? Not suitable for highly viscous flow and high initial cost and installation complexity. Now I will derive the discharge equation for this Venturimeter. How to find the discharge through this Venturimeter. This is Venturimeter. Here manometer is fitted in this Venturimeter. Rho f is the density of the flowing fluid. P1 upon rho g plus Z1 is piezometric head at point 1, and P2 upon rho g plus Z2 is the piezometric head at point 2. Point 1 is in the pipe and point 2 is at the throat, and density of the manometric fluid is rho m, which is greater than the flowing fluid. Here H is the piezometric head difference of the flowing fluid. This is piezometric head at point 1 and this is piezometric head at point 2, so this difference is H. And in real fluid, H will be more than the ideal fluid H. So area at this section will be pi by 4 d square. D is the diameter of the pipe, and area A2 is pi by 4 dt square. Dt is the diameter of the throat. Now we know that discharge is A into V, that is constant. From here and here discharge will be constant. So Q equal to A1 V1 equal to A2 V2. From here V1 equal to Q by A1 and V2 equal to Q by A2. We know that piezometric head is equal to P upon rho g plus V square plus P upon rho g plus Z. This is piezometric head. So piezometric head difference is equal to h between 0.1 and 0.2. So now I am going to apply the Bernoulli equation between 0.1 and 0.2. So P1 upon rho g plus V1 square upon 2g plus Z1 equal to P2 upon rho g plus V2 square upon 2g plus Z2 plus HL. I am considering the losses also. So here now rearranging the terms, V2 square minus V1 square upon 2g equal to P1 upon rho g plus Z1 minus P2 upon rho g plus Z2 minus HL. So this term is H. So here it will be H minus HL, and putting the value of V2 and V1 from here, that is V1 equal to Q by A1 and V2 equal to Q by A2. So here I am putting this value. From here I can calculate the Q actual value. So after solving, this Q actual is coming to this one. So from here after solving I came here, this Q actual equal to A1 A2 into root 2g H minus HL upon root of A1 ka square minus A2 ka square. So when HL is 0 means there are no losses, then the discharge will be theoretical discharge, means no losses are there. So Q theoretical will be A1 A2 into root 2gh upon A1 ka under root of A1 ka square minus A2 square. This is theoretical discharge. We know that the coefficient of discharge CD equal to Q actual divided by Q theoretical, which is H under root of H minus HL, means this divided by this, we will get coefficient of discharge, and coefficient of discharge is maximum for Venturimeter, which is 0.95 to 0.98, and head loss is inversely proportional to coefficient of discharge, means if coefficient of discharge is maximum, then head loss will be minimum and cost will be maximum. If coefficient of discharge is maximum, then cost will be also maximum. That's why this Venturimeter is costly. And Q actual will be, from here we say that Q actual will be Q theoretical into CD. So Q actual equal to Q theoretical into CD. Q theoretical is this one, A1 A2 into root 2gh upon under root of A square minus A2 square into CD, that is written here. And we can say that this is Venturi constant, A1 A2 into root 2g upon A1 ka square minus A2 ka square ka whole root. Now when manometer is connected in Venturimeter, here manometer is connected in this Venturimeter, so there will be some deflection in this manometric fluid when the fluid is flowing from this pipe. So using this deflection we will calculate this piezometric head difference. So by solving this, P1 plus this distance, P1 plus rho fluid, here this fluid is flowing, so rho f into G into this distance will be Z1 minus H0. Here I am taking reference line, so from we are going to down, this will be positive, and when we are going to upside, then it will be negative. So here this is rho f plus G into Z1 minus H0 minus, we are going upward here, rho m into G into this is Y into G, this one minus this distance. So this distance will be Z2 minus this H0 plus Y, means this plus this, Z2 minus this plus this. So here I am writing rho f into G into Z2 minus Y minus H0. So I am getting this one equal to, here pressure is P2, or we can also say that here this is reference line, so at this reference line the pressure at this point and this point will be same. From here and here we can calculate the pressure at this point and this point will be equal, also we can calculate from here. So after rearranging, P1 minus P2 equal to this rho m, we are shifting these these terms to this side, so we will get this equation. From here rho f into G into H0 will be cancelled out. So after rearranging, P1 minus P2 equal to rho m minus rho f into G into Y minus in bracket Z1 plus Z2 into rho f into G. So after dividing by rho f into G, so we will get P1 upon rho f into G minus P2 upon rho F into G equal to rho M divided by rho F minus 1 into Y minus bracket Z1 plus Z2. So by placing the Z1 to this side, Z1 plus Z2, here P1 upon rho F into G plus Z1 minus P2 upon rho F into G plus Z2 equal to Y into rho M upon rho F minus 1. So this is piezometric head difference. So H will equal to Y into rho M upon rho F minus, this is 1. So if the Venturimeter is horizontal, then Z1 equal to Z2. So P1 upon rho F minus P2 upon rho F, P1 upon rho F into G minus P2 upon rho F equal to Y into rho M upon rho F minus 1. So means is on Q actual will discharge will be Q actual will be CD into A1 into A2 into root 2 GH upon under root of A1 guy square minus A2 square. Means we can say that when manometer deflection is same whether the pipeline along the with the pipeline along with the connection is horizontal or not. Means it is at angle or horizontal, it will not affect the H manometric deflection and this discharge will be same. And if the flowing fluid density is more than the manometric density, then H will be Y into 1 minus rho M upon rho F. Here rho M is the density of manometric fluid and rho F is the density of the flowing fluid. So here rho M is less than rho F, H will be this. That's it.